Well, good morning and happy St. Paddy's Day for all of you who are Irish and all of you who are not Irish. Last day
I see you're wearing green, by the way. I see you're wearing green.
I am wearing green. And as I pointed out, in my entire lifetime, I don't think I've made it 5 times in my entire lifetime. Actually remember to wear green. And in fact, at Mesa College, every year, the same people say, "You forgot again?" Every single year. I'm like, forgot? Oh yeah, that's right. So I actually changed my shirt this morning after I got up. I actually had a different one. Wait a minute, I have the opportunity to get this right. Finally. I can honestly say I've been at Mesa for 35 years. I don't think I've ever worn green once in all of that time. But I got it right today. Okay, last day we were asked to do a couple of different proofs, and one of the proofs was, I believe, it was this. We said we want to prove that this is never divisible by 3 for any integer n. And the way we were going to prove that is by contradiction. But the first mistake some people make was they said, okay, let's assume this is always divisible by 3. No. That is not the complement at all. The negation of this is always divisible by, or excuse me, the negation of this is never divisible by 3 is there's at least one case where it is. And so several people set it up to say, I'm going to prove it's always divisible by 3. And then I found a counterexample. No, it doesn't work that way. You're saying, let me assume there is one case where it is divisible by 3 and then show that fails. That's a contradiction. There's no counterexample in proof by contradiction. It's completely missing the point. The second problem, I think it was 4 plus 3 root 2. I think that's what it was. And we're asked to show that this is irrational. So what we did was, of course, we started by assuming it is rational. And I got some people saying, all right, well, let's assume this equals k and it's rational, but this is irrational, so there's a contradiction. What? If I'm assuming it's rational and I don't write anything else, I haven't got a contradiction. First of all, this is not even remotely close to what you're doing. No, you don't assume it equals k. What's k? A lot of folks just said it equals k. I don't know what k is. We never defined k as being anything. It just equals k, and k is an integer. No, k is rational. Well, then it should be a quotient of integers, and then I'm going to get a contradiction. But here's one of the things that some folks did. I told you guys we can use the fact that we've already proved that that's irrational. So what most of you did was you isolated the root 2, and then you wrote something correct, and then you were able to get a contradiction. But here's where we got in trouble. Several people said, well, I'm going to prove this is not rational because 3 times root 2 has to be irrational, and then 4 plus 3 root 2 is irrational, which, by the way, mathematically, we know that's true, but why is 3 root 2 irrational, and why is 4 plus that? And so what's happening is a lot of folks are quoting and citing theorems that they've never heard of, never seen, and actually aren't theorems. I had more than one person tell me, well, 3 root 2 is irrational because everybody knows the product of a rational and an irrational is always irrational. Really? 0 times an irrational is irrational? No, that statement is absolutely false, period. And the other one was, well, everybody knows that the sum of a rational and an irrational is irrational. Well, that may be true, but I've never seen a proof of that in my entire life. And that's not actually a theorem that I'm aware of. So citing that as the reason for your answer when you've never seen it and it might not actually exist, even it might be true, that's true. Pi raised to any power is irrational. I know that, except 0 power. Yeah, there's no proof. There exists no proof that that's a true statement, even though it's common sense. So you can't use theorems that don't exist, or just, I don't think it's true, so therefore it's not true. So that one, most of you did a great job. And the funny thing is I did the proof in class, almost the exact same problem, and most folks just piggybacked on that. That made it a little bit easier. Okay, so today, we're going to do some manipulation with sequences and some series to just sort of play with the algebra and just to get a basic feel. Now, this is not Calc 2, where we're looking at series and trying to determine convergence or divergence of series using all the various tests. That's a totally different animal. That is so that you can use power series to solve a differential equation. That's why you did series in Calc 2, so that you can use them in diffie-qs to solve problems. That's not our goal. We're interested in what are called, again, recursive definitions. Recursive. Okay, and I just started sequences yesterday in my Calc 2, and it's not terribly different from the stuff that we did last day in this class. Now, a recursive definition is one where you're defining things in terms of previous things. So for example, we know that an arithmetic series, an arithmetic sequence is one defined this way, that the n plus first term minus the nth term is a constant difference. So remember what the subscripts mean. The subscripts mean, first of all, n is the index, it's the counter. And generally we have a first term. So it usually will start at A1. Now, there are situations where you could start later. There are situations you can actually start at 0. But for now, we know A1 and so on. So A2 minus A1 is constant, A3 minus A2. So if I had something like this, 2, 5, 8, 11, on and on and on, 5 minus 2, 8 minus 5, 11 minus 8 is always the same value. Another way of saying this is the n plus first term is equal to the nth term plus d. That's the same statement. That's saying, oh, I'm counting by the same number. So we learn this in baby algebra. We don't spend a lot of time, but it's a really handy one because it's a recursive definition. Now, the problem with the recursive definition is real simple. If I want to know what's the 100th term, then that means I'm actually required to know the first 99. And that is not entirely practical. I need the millionth term, please. Okay, well, let me generate the first, you know what. So one way to get around this is it's often the case, not always. In a recursive definition, you can actually find a general way of stating it. The only thing I would need to know is what is the constant difference? And I absolutely have to know what is the first term. So let's suppose I was looking at this guy right here. We agree this is definitely arithmetic. And the first term I can see is a 2, and the constant difference is a 3. Then what does that mean? Well, that means that the second term in these terms is 2 plus 3. But the third term would be 5 plus 3, or 2 plus 2 times 3. And the fourth term, which would be 8 plus 3, or 2 plus 3 times 3. Right, we see that, oh, if I do it like this, then eventually I can say the n plus first term is what? The first term plus n minus 1 times 3. Okay. Why n minus 1? Because I haven't added the 3 yet on the first term. I don't add it until the second term. So if I simplify this, that'd be 3n minus 1. So for this particular sequence, let's see, if n is 1, I get 2. Yes. If n is 2, I get 5. Yes. I can see that works. This is a vastly superior way of working with this sequence, because now if I say, what's the millionth term? You can say, well, it's 3 times a million minus 1. I don't have to find anything prior. So manipulating recursions is actually a very powerful thing. And you can't always do it, by the way. Okay, there are recursions that are just complicated enough that you're not going to be able to come up with a general formula. But when I can come up with a general formula, and the most common ones were the arithmetic and the other one being the geometric. Okay, I'm not going to go over that one. Most of you remember that one. But are there other sequences that are considered very, very powerful that I may have a difficult time with the coming up with a general? Well, most of you are aware of the Fibonacci numbers, sorry, the Fibonacci numbers. And I love these. If you're not that far removed from high school, think back to probably your science classroom. You probably had a poster with the pictures of different things with the Fibonacci numbers. Anything in nature that has a spiral pattern like pine cones. Okay. What's another one? Honeycomb. My favorite, sunflowers. I actually had sunflowers and I actually looked, and they have a spiral pattern with the numbers. Trees, no, those are concentric circles. But things with spiral patterns in general, the Fibonacci numbers we know look like this. Where are we? 13, 21, 34, and so on. So if you remember what the Fibonacci numbers are, the n plus second term is always equal to the n plus first term plus the nth term. I add the two previous terms to get to the next term, forever and ever and ever. But in this situation here, knowing the recursion is one thing, but I'd also have to know, I can't tell you the third term is the sum of the first two unless I tell you what the first two terms are. So in this case, we'd say an A1 and A2 are both one. I would have to give you this because if I change A1 or A2, it changes the entire sequence. Now, the author shows you there actually is an nth term. There is a way in this recursion to tell me what's the 100th term without having to find the first 99. Now, I used to teach programming classes at Mesa, and one of the assignments I'd always give students is, all right, here's the Fibonacci numbers, write me a program that generates them. And everybody could do this. It was a really easy thing to write. But by the time I said, okay, now tell me what the first 100 numbers were, it would come crashing down because it was astronomical, the number of calculations required to do that, because the third number, you have to calculate the first two. The fourth number, you have to recalculate the first three. The fifth number, you have to recalculate the first. There's no way you can use prior knowledge. It kept recalculating. And so if I said, well, what's the 1000th number? Well, it might take a month. I mean, it was ridiculous how long it would take. So there is actually a formula. I'm not interested in going over that. The author presents it to us. It's a clever formula that generates all the numbers, rather than the recursion. But when I have a recursion, recursions are really easy to use if I'm just interested in finding one value. So let's do a simple example of generating numbers with the recursion. All right, let's suppose, let's see, I printed one out for myself. Let's suppose that I have a n plus 1 equals n times an plus n squared. Okay. And I'm going to tell you that A1 is 2. Let's find the first few. And by the way, it's implied here that I'm going to start with 1. Okay, so I'll put in parentheses, n is greater than or equal to 1. It is possible that I can say that the sequence doesn't start until, the 10th number. Technically, n could be negative. You're just never going to do that. That doesn't really make sense, because the concept of a sequence is there's a first term. There's not a 0th term or a negative 5th term. That doesn't kind of go together. In a series, we often do that. So if I ask you, what are the first few terms of this? Well, let's see. Based on this recursion, this definition here, I can say then that what is A2? Well, that means I'm replacing n with 1. So that'd be 1 times A1 plus 1 squared. Okay, but A1 was 2. So 1 times 2 plus 1, so that'd be 3. Okay, so now what's A3? That means I'm replacing n with 2. This is where we sometimes get in trouble. When I say A3, my brain says replace n with 3. No, the subscript has got to be a 3. So I'm replacing n with a 2. So this would be 2 times A2 plus 2 squared. A2 was a 3. So 2 times 3 plus 2 squared, that'd be a 10. A4, well, that's going to be 3 times A3 plus 3 squared. Oh, okay, 3 times 10 plus 3 squared. We'll do one more. And then A5, that's going to be 4 times A4 plus 4 squared. Oh, like that. Well, 4 times 39 would be 156 plus 16 be 172. And I think we can see at this point, the numbers are going to start getting really big, really, really fast. But this is how we would generate the first few terms given this recursion. It's not all that complicated. Right, I just got to make sure. Now, if I make any error along the way, then every number after that, of course, would be completely different, because it's like I'm changing the definition of that particular sequence. Okay, so this is just an exercise in manipulation. There's nothing about the final result that it's entirely critical. It's just the how to find the final result part. Now let's do one maybe a little bit more complicated. Let's do one where the recursion involves more than one. Let's suppose I have a recursion, let's say A n plus 2 equals, let's see, how about 2an plus 1 plus n times an. A1 is 1 and A2 is, let's say, 2. I always like to start with small numbers, otherwise this can get out of control really fast. Okay, so with that, my first calculation obviously would be for A3. So A3, which would be replacing n with a 1, would be 2 times A2 plus 1 times A1. Now, could I just go ahead and insert the numbers? Of course I could, but I'd rather see the pattern. See, if I don't do anything else, I can certainly write down the first few, because this is now going to be, what's A4? Well, that's going to be 2 times A3 plus 2 times A2. What's A5? Well, that's going to be 2 times A4 plus 3 times A3. See, I can write that down before I even insert the numbers. Now I'll go ahead and insert the numbers. So 2 times A2, so it's 2 times 2 plus 1 times 1. If I did that correctly. Okay, that's A3, so that's what's going to go here. So now this is 2 times 5 plus 2 times 2. Okay. And my A4 is 14, so this would be 2 times 14 plus 3 times my A3, which is 5. So as long as my bookkeeping is good, this is why I would prefer to write it in this form, because I can kind of keep track. I can see that, you know, the pattern here is really clear, and then I can plug in my numbers. That's probably an easier way to set up the problem. So this is just a very, very simple exercise in manipulation. There's nothing incredibly important about this. It's just the how. So now let's work a problem where we actually have to do some work in order to find the answer. I really like this next one. It's kind of fun. Okay, fun, I guess is relative, but I like it. So let's suppose I'm going to define a recursion as follows. I'm going to define an equals 4 to the n minus 3 to the n for n greater than or equal to 1. Now, the nice thing is I'm giving you a general term here. So if I ask you what's A1, A2, A3, A4, you can easily tell me. You can tell me anything by just throwing it in. But what I want to do is show, I want to prove that an plus 2 is equal to, one second, trying to read my own writing, 7an plus 1 minus 12an. Given this definition of an, I want to prove this statement is true. Ooh, now that's kind of interesting. Now, by the way, the direction we're going is a heck of a lot easier. If I started with this, I don't know that I could derive this. That's too complicated. But if I start with this, it's probably easier to go this way. So you say, how in the world can I get from point A to point B? Well, I know what an is. Therefore, I automatically know what an plus 1 is. Replace n with n plus 1. I know what an plus 2 is. Oh, okay. So I can replace the individual pieces and see if I can come up with the conclusion. So based on this first definition, okay, what do I know? Well, if an equals 4 to the n minus 3 to the n, then an plus 1 would have to be 4 to the n plus 1 minus 3 to the n plus 1. And an plus 2 would have to be 4 to the n plus 2 minus 3 to the n plus 2. I can absolutely say that because this is the definition. Okay. Now, I'm trying to show this is true. I don't start with that statement being true and then try to work backwards. A lot of us make that mistake. Whenever you're asked to prove something is true, you don't start by assuming it's true, because if you do, well, then you're already done. Okay, no. I want to take either the left side and see if I can conclude the right side, or take the right side and see if I can conclude the left side. And most of you, if you go back to trigonometry when you're trying to verify identities, the simplest rule of thumb is always take the more complicated side, because then you can whittle it down and simplify it. If you take the easier side, it's harder to beef it up. In other words, it would be harder for me to start with this statement here and work backwards. It'd be much easier to insert these guys into here and see if I can conclude that. Okay, that's just a simple strategy. It wouldn't matter which way you go, but you don't start off with the whole statement and then say, let me just work both sides, or no. In fact, the working both sides part is not mathematically valid ever. I can take something that's not true and easily prove it's true if you allow me to work both sides, because there's all sorts of magic you can do. There's a lot of cheating you can do. No, can't do that. So let's start with this. So 7 times an plus 1 minus 12 times an is what? Well, it's 7 times this minus 12 times this. Oops, not an, sorry. 4 to the n. All right. So that's my starting point. Now, what do I want to do with that? Well, with that, I want to manipulate it. If nothing else, let's manipulate it in such a way that we get the ANs by themselves. I mean, excuse me, the 4 to the n's and the 3 to the n's by themselves. It's going to be harder to make this term look like this term, but it'll be easier to make this one look like this one. See, I can pull down one of the exponents. So that would be 7 times 4 times 4 to the n minus 3 times 3 to the n. You see. Now I know that statement's true. So now algebraically, if I thought of 4 to the n and 3 to the n as being x and y, then how many x's do I have and how many y's do I have? So what are the coefficients, in other words, in front of 4 to the n right now? So right now I have 7 times 4, 28, minus 12. So right now I have 16 times 4 to the n. I have negative 21 plus 12. That's negative 9 times 3 to the n. Okay, so whether this statement is true or not, whether this is true or not, this statement here is equal to this, is equal to this, is equal to this. That I have no doubt of. In fact, if you had just made up any 2 coefficients whatsoever, you could still do exactly what I did. But here's the beauty. Look at that guy right there. Isn't that equal to 4 squared times 4 to the n minus 3 squared times 3 to the n? And why is that a cool thing? Because that's equal to 4 to the n plus 2 minus 3 to the n plus 2. And I do believe that is the result we were shooting for. Right, crowd goes wild, confetti everywhere, dancing in the streets. It's all good. So starting with this, I concluded this. That was my goal. Well, where did this come in? Well, that was the definition of my recursion in the first place, or the definition of my, I should say, my sequence in the first place. And then that's it. I left it alone in order to derive the other things. So this is a really nice exercise in being able to manipulate basically the rules of sequences. So that's kind of a cool one. Now I want to go into series, because in the big picture, series are a lot more important because they're used just so much more often. Now, I should say I should say it differently. A series, in case you forgot, a series is the sum of the terms of a sequence. So I always laugh when people, even in calculus, they'll say, well, we're going to work with the infinite series as opposed to the finite series. The word series means infinite sum. That's the people who say, well, I'm going to work with the straight line. And you always hear math people say a straight line. You really have to throw in the word straight, because there can't be anything else. That's, to me, I'm sorry, the round circle. I mean, it's kind of a silly sound. So what is a series? A series is an infinite sum, but it's not practical to do the infinite sum. And so we saw last day, we were talking about what are called partial sums. So I want to remind you of some of the rules of series. Again, this is from a manipulation standpoint. So one of my favorite stories, and if you had calc from me, I go over this. So one of my math heroes is little Carl Friedrich Gauss, and he lived a couple hundred years ago. and he was a smart guy, but apparently he was an obnoxious brat as a kid. So the story, which is legend, and by the way, legends don't have to be true, right? Because the whole point of a legend is kind of to make a point about something, right? There's a lot of legends in different cultures of things. I mean, Mulan. Is any of it true? Oh, I'm sure something's true, but it doesn't matter. It's a great story. So the legend of Carl Friedrich Gauss as a child, in the one-room schoolhouse where you have all the kids of different ages, and they had their little easel that's like a chalkboard and their piece of slate, the granite, they wrote on there, say, well, why didn't they use pens and pencils? Well, they hadn't been invented, not from mass, what about paper? Paper didn't exist in that capacity, for everybody to have. It's not like you could go down to home Office Depot and buy stuff 200 years ago, So the teacher, supposedly, to keep him busy, said, I want you to add up the first, million natural numbers, 1 + 2 + 3 + 4. So, okay, I keep him busy for, at least a while. And of course, a couple minutes later, he comes back with an answer. And by the way, the calculators weren't very good back then. See, a calculator was a sandbox with a stick that you kind of wrote in the sandbox. That was your calculator. Okay, so the question is always, how did he do it? Well, this is actually how we derive some of the formulas we derive. So he did, well, 1 + 2 + 3 + ... let me say 99999 plus a million. He did this. And he says, well, if I write the numbers in reverse order, there's my mil, and then there's my 99999 and so on. If I write my numbers in reverse order, it would look like that. And then he noticed, and if I add that, that's 1,000,001. And that one's 1,000,001. And that one's 1,000,001. I think you kind of see where this is going. And that one's 1,000,001. So he noticed that if I just write the numbers in reverse order and I add them vertically, I'm going to have 1,000,001. Now, how many times am I going to have 1,000,001? I'm going to have 1,000,001 a million times. Now, is this the answer, folks? Oops. Is this the answer? Anybody?
No,
Not quite. Why?
because you gotta divide it by 2.
Because I just did it twice. So this is the answer. And so little Carl Friedrich comes back with the formula, right? He's like, oh my gosh. Now, I love Gauss because most of linear algebra is, I'm a big linear algebra guy, and he did most of the work on modern linear algebra that we have. But he was also a brilliant mathematician, also contributed a lot to the calculus and everything else. Sometimes this is referred to as Gauss's formula. And what it was is, if I have a sum of an arithmetic, that's an arithmetic sequence, okay? But what he did was he said, well, the sum of the first n natural numbers is simply n plus 1 over 2. And if you guys remember, I mentioned this last day when I did, remember the sum of I squared, I cubed, and so on. This was one of the ones I mentioned. Well, it comes directly from here. N is 1,000,000. Boom. But what's more important is, what if this is an arithmetic series in general? Well, I want what's called the nth partial sum. I'm not adding this forever because that would be infinite. I'm adding up the first this many terms. So often this is referred to as S sub n, S being the infinite, S sub n being the sum of the first n terms. And that's pretty universal notation right there, just to make life easier on us. So in general, could we find a way of taking something like this and doing this? Well, think of the arithmetic. Okay, the arithmetic. So A1, and then the next term was A1 plus D, and then the next term was A1 plus 2D, and so on. The nth term was A1 plus n minus 1 jumps of D. Well, what if I wanted to add this many? I wanted to add the first n terms. Well, using the same reasoning, if I add the first term to the last term, if I add the second term to the second last term, and so on, I'll use the example we did earlier. I'll say I want 2 plus 5 plus 8 plus 11 plus 14. Let's say we go up that far. I want to go that far. I'm counting by threes. Well, the sum of these two is the same as the sum of these two is the same of the sum of these two, because as I'm going up by three, I'm also going backwards by three if I reverse the order. So the same rule applies in general with an arithmetic series. If I want the sum of the first n terms, all I have to do is take the sum of the first and the last. Well, what's the last? That. Okay. But we usually just say, we'll call that the nth term. Oh, okay. And then what am I going to do with that? I'm going to multiply it by n and then over 2. This is exactly the same thing. My first term a moment ago was 1 and my nth term was 1,000,000. Now my first term is whatever it is, and then my last term is the nth term. This is the sum of the first n terms of an arithmetic series. Okay, that's very practical and useful information. That one's not nearly as common though as the one for the geometric. And again, we all hopefully remember doing stuff like this in algebra to be able to manipulate series. So the geometric, if you remember, the geometric is one where the nth term, excuse me, sorry, let me go back to the original. For the geometric, the definition of a geometric is that the ratio of consecutive terms is a constant. We use R for ratio. This would imply then that the n plus first term is the nth term times R. So if you remember how this works, well, if my first term, then my second term, then my third term, my nth term would look like this. Okay. Now the sequence goes forever, but if I said I want to add up, this would be the nth term because I don't start the R until the second term, right? Third term has an R squared, fourth term has an R cubed. If I wanted the sum of the first n terms, then I want to do this, right? I'll write it like this, A1R minus 2, and then A1 R to the n minus 1. I want to add these guys up. Now, unlike the arithmetic, I can't just take the first and the last and manipulate those because these are not a constant sum, it's a constant product. So an example of this might be, I have 2 and then 6 and then 18 and then 54 and then 162. I'm multiplying by the same amount, but I can't do this. That won't work, right? Because it's not a constant difference. So the trick for this one, and again, this is just one of these brilliant mathematicians who came up with this saying, well, you know, I got to add up a large amount of numbers and always assume that n is large. So in other words, there's only 3 numbers here. I can just add them up. What if there's 3 million numbers? How would you add them up? If I said take negative r times Sn, what would negative r times Sn be? Well, then it'd be negative A1R, negative A1R squared, negative ... negative A1R to the n minus 1, negative A1R to the n. I'm going to take every one of these terms and multiply it by negative r. And then what you notice is all the way down the line. Now, if I said add these up, on the left side, I have Sn minus Rsn, and on the right side, every single term will cancel except this one and this one. So one of the questions on your most recent quiz, I gave you a telescoping series where when you start writing out, you realize, oh God, every single term cancels except the first and the last. And that's what made it doable. So I get A1 minus A1 R to the n. So if I go back up to the top, and again, I'm sure all of you have seen this in your life. You may not remember the details. My goal was to find Sn, which I think I can do now. So if I factor Sn out of the first term, I'd have Sn times 1 minus R. And if I factor the A1 out of the second term, I'm going to have 1 minus R to the n. So then Sn is simply this. Now, most of us recall this from algebra. We've used this in Calc 2. the nth partial sum, or the sum of the first n terms of a geometric series where the first term is a1 and the constant ratio is r, is this. Now, the nice thing is if the r is between -1 and 1, in other words, if the absolute value of r is smaller than 1, we know this term approaches 0. So then I can actually calculate the infinite sum. So what's the infinite sum of a geometric series? If the absolute value of r is less than 1, we show this in calculus that this term approaches 0 when the absolute value of r is less than 1. If it helps, take 0.999 on your calculator and raise it to the millionth power, and your calculator will spit back a 0. It isn't 0, but it's so small it can't be measured. So we know this is simply a 1 over 1 minus r. This is one of the most practical reduction formulas we know. This is why when you do, the old, well, I'm going to walk halfway across the room, and then I'm going to walk half of that, and then I'm going to walk half of that, and then I'm going to walk half of that, right? That's actually the nth one. But I'm going to do this forever. Well, first of all, do you ever reach the other side? No. But the difference between you and the other side is getting smaller and smaller and smaller and approaching 0. So if I actually could do this forever, in calculus, we can always do it forever, then what does this add up to? Well, my first term is a half. My constant ratio is a half. And that's equal to 1, as we know. Okay. One of my favorite identities that comes directly from this, a lot of people don't realize this is a fun one. Now, you guys know what happens when you put a bar over. A bar means that that number continues forever. If you put a bar over more than one number, then that sequence of numbers. So we know what this means. This means 0.999 ... forever, never, never. I'm going to make a crazy, outrageous claim. This is identically equal to the number 1. What? There's exactly 3 easy ways to prove this. 0.99999 equals 1. No. You can't do that. It rounds off to 1. No, I'm saying the infinite decimal. Now, there's 3 ways. The most complicated way would be this. What's 1 minus this? Well, in general, if I said 1 minus, 0.9, you'd say that's 0.1. If I said 1 minus 0.99, you'd say that's 0.01. If I continue this pattern, I think we all agree that that's a true statement, what I have right there. Okay. So then what is it if it's forever 9s? Well, wouldn't that mean that this is forever 0s before I reach my first 1? If it's forever 0 before I reach my first 1, will there ever be a first 1? No, because it's forever 0s. I never actually get to the 1. That's the first proof. Okay. The second one, this is a geometric, 0.9, which is, remember, that's this. You may have done things like this in algebra or calculus before. 99999 is 0.9 plus 0.09 plus 0.009 forever and ever and ever. That makes it a geometric series. How is that geometric? Because my A1 is 0.9 and my constant ratio is 0.1. By the way, this is absolutely correct. That goes forever, and every time I'm moving the decimal 1 place. So according to the formula we just showed, this equals first term over 1 minus r. That's the second proof. That's a very mathematical proof. Then the third one is the ODA proof. We like ODA proofs. That means duh, that's what I mean by ODA proofs. What is 0.3 the same as? Well, we know that's 1/3. What is 3 times 1/3? Well, that's 3 times 0.3, which would be 0.9. We're done. 0.9 with a bar is 3 times 1/3, period. Because that's what that means. Now, the point is, these are calculaic kind of arguments. No, really they're manipulations of series. So being able to do these crude types of manipulations is just, it's useful in general, okay? I'm not interested in this class. I'm not interested in the calculus aspects, but I am interested in the number crunching aspects. So now we're gonna look at one more type of problem, and that's the combinations, things involving factorials and stuff, okay? Now there's a classic problem, it's called the inclusion-exclusion formula. And I want to make this really, really simple. Okay, I have a group of, let's just keep it simple. I have a group of 40 people in this class. There are exactly 40 people. All right. And I want to form a committee of, let's say, 5 people. And this committee is going to be the oversight committee. You know, they're going to make all the important decisions, like, you know, when are we going to have a year-end party? You know, what sort of, you know, games should we be playing on Friday nights? You know, just the important stuff like that. So I want a committee of 5 people. Now, you all know if I have 40 people and I want a committee of 5, if you're chosen first, second, third, fourth, or fifth, you're on the committee. There's no order there. Just being on the committee is what it is. So if I said, how many ways can you do that? The number of ways would be 40, choose 5. Okay, that's a combination. And on my calculator, I would just do it. But if I was writing it out, we know that's what it equals. But I would just simply enter that onto my calculator. Okay, great. Now, Alexei, it's important. He's either on the committee or he's not on the committee. That's all that matters to him. Okay, I'll use Alexei as my example. Alexei's either on the committee or Alexei's not on the committee. Now, would you agree that every committee that could possibly be formed either has Alexei or it doesn't? That should make perfect sense to you. Exactly how many committees have Alexei on them? Well, that means Alexei's on the committee and I need to pick 4 other people. By the way, this exact same mathematics is used with cards if you're talking about poker. So Alexei's on the committee, but I must have 4 other people. So how do I have 4 other people? Well, wouldn't 4 other people be 39 choose 4? Because Alexei's already on the committee, I need to pick the other 4. Okay, to match him with Alexei. 39 choose 4 because I'm picking them from the remaining 39 people in the class. These are all of the committees that Alexei's on. How many committees is Alexei not on? That means I picked 5 people, but he wasn't on them. So I picked 5 people from the other 39. And my claim is that these are exactly the same. Whoa. Now, to verify this, let me grab a calculator. By the way, the calculator is not the proof. The calculator is the verification of the truth of this statement. The truth is a little bit different. How we prove it's a little different. So the first one is 39 choose 4. My calculator says that's 82,251. The second one was 39 choose 5. My calculator says that's 575,757. Yikes. And the last one is 40 choose 5. My calculator says that's 658,808, which, by the way, if you do a quick check, is in fact the sum of those two. So this is a really cool little thing that I just did. This is called, often referred to as the inclusion-exclusion formula. In other words, all the committees that Alexei was on included, and all the committees that he was not on excluded. So does this present a formula in general? Yes. And this formula is considered hugely important. In general, n choose r. Now, take one element of the group of n. How many ways can that element be in this? That means I need to pick the other r-1 elements from the remaining n-1 elements, plus all the ways that one element cannot be in this group, which would be n-1 choose r. So in other words, that's the formula I just did. So our goal would be, how do you prove that? Now, when I talk about a proof, there are 2 types of proofs. There's basically just the brute force, let's just write it out and use the factorials and prove it. That's absolutely always correct. And then the second one is what we often refer to as a combinatorial proof. In other words, I'm going to give you an argument. And the argument I just said was, well, if I take any one item, it's either in the group or it's not in the group. These are all the ways for that item to be included. These are all the ways for that item to be excluded. And so therefore they have to add up to the possible choices, just like in the Alexi example. And that is true. That one's harder to convince people of because you're saying, well, how do I know you're right? How do I know these? So what we want to do, the simple exercise, I want to prove this algebraically with the factorials. So now the question is, should I go left to right or should I go right to left? The answer is it doesn't matter, but which might be easier algebraically? And again, going back to, it may be easier to take the more complicated of the two, put them together. So I would probably opt to show that this side equals this side. You can go the other way, but undoing it and making this into a sum might be really difficult. So let's prove this. By the way, there's nothing about this that's ridiculously important. It's the process of how do I prove something like this using my factorials and such, and because that's kind of where we are right now. So n-1 choose r-1 is equal to n-1 factorial over n-1 minus r-1 is n minus r factorial. Okay, and then r-1. Now, if all else fails, n minus r plus r-1 has to add up to n minus 1. Remove the factorial for a second. So if I said 40 choose 5, my denominator was 35 factorial, 5 factorial, because there were 5 that were in, there were 35 that were not. That's one way of thinking about it. Okay. So I want to pick r-1. So r-1 are in and n minus r are not. But if I add those together, yes, that does work. Very, very important because the minus, right? I can easily mess up one of those by not thinking about it. I might have an r plus 1 by mistake, for example. And the second one was n minus 1 choose r, which would be n minus 1 factorial over n minus r minus 1 factorial, r factorial. Okay, now I want to add these two quantities together. So n minus 1 choose r-1 plus n minus 1 choose r, of course, will now be n minus 1 factorial over n minus r factorial, r-1 factorial, plus n minus 1 factorial, n minus r-1 factorial, r factorial. Well, I would really like to have a common denominator. A lot of you say, well, I can factor the n minus 1 factorial out of my numerator. I can. It's not really going to make any difference. I still have a sum. I need this to be one quotient. So how do I make it one quotient? Well, first of all, n minus r minus 1. This is bigger. So I need to multiply this by the appropriate term to make it look like this. And quite frankly, I know that n minus r factorial equals n minus r times n minus r minus 1 factorial. So that means if I multiply this term by n minus r, it will look like this term. So the first thing I'm going to do is multiply top and bottom. I'm going to go n minus r, n minus r. I know it's kind of squeezing it in there. Okay. Now, r factorial is bigger than r minus 1 factorial. So similarly, r factorial equals r times r minus 1 factorial. So I need to multiply this term by r. So I'm going to go r over r. There's a little bit of a squeeze there. When I do that, the next thing I get ought to make it easy for me to finish this problem. So now I have r times n minus 1 factorial plus n minus r times n minus 1 factorial all over, because I just made it. This is now r factorial. This is now n minus r factorial. Everyone, hopefully you see that. By multiplying this by r over r, I made that guy r factorial. By multiplying this, I made that one n minus r factorial. But I have the stuff on top. Now might not be a bad idea to factor out the n-1 factorial from the top. I have r of them plus n-r of them. I have n times n-1 factorial. That just gives me n factorial on top. And that, folks, is our result. So we did it. So this is a really nice way to manipulate something, okay? And again, there's nothing about the final formula. There's nothing about that that's critical information. It's all about the manipulation. Now, if one of the classes that this is a precursor of is a class called combinatorics. When I was a student, that was probably what I had the most background in, both as an undergrad and as a grad. That was one of my passions. Most people think I'm the linear algebra guy. Yeah, I am that too. Linear algebra and combinatorics were my two fields in grad school. Those are what I took my qualifying exams in at UCSD. And the problem is I don't get to teach combinatorics. I teach linear algebra. Combinatorics, everyone thinks of combinatorics as simply, you know, factorials and combinations. Well, that's a piece of combinatorics, but that's not all of it. Combinatorics is a very broad field. In fact, if you're a computer scientist, it's probably the most important type of math because of the way you calculate and the logic used. I'll give you an example of one of the things that one of my professors presented before the first day of class. He said, you've got a whole bunch of items and you need to put them in a box. And let's say the items are all, you know, rectangles, rectangular shapes, keep it simple. But when you put them in the box, you have area left over. They don't fit tightly in the box. But most of us would do the exact same thing. We would arrange everything by rows, you know. So let's say I'm putting a bunch of items that are exactly the same shape into the box, keep it simple. And then we'd make everything rows and you know, that just kind of the logical way, but I have cushion space left over. And he said, is this the most efficient way? Or perhaps if I just randomly put them in and maybe rotate them slightly and can I get more in the box? The idea being, imagine the area or the space that's left over. We want to minimize that. And so the idea, and he showed us then that you could prove that by doing it differently, you could fit more items in the box. And it's like, whoa, and no joke. It was the first time in my entire life I actually he used the term thinking outside the box. And this was many years before I heard another human being coin that term. So I think he actually is credited with that term because he had a box and he wanted us to think differently. I don't know if it was unintentional or accidental, the whole outside the box. But the idea being, how do you think differently from the standard way of doing things? One of the problems that I had in grad school, I remember this was really different, is sometimes called the hat check problem. The problem's actually in French, and I still have my original solution. You have N couples going to a party, and this is supposed to be back like a long time ago because I believe it's a French problem. And you know, the men are wearing their fedoras and the women are wearing whatever their nice hats are, and there's a person at the door checking your hats, the hat check person. Like there's actually a job where people did that. And so I'm handing my hat and my wife is handing her hat, that kind of thing. So you have N couples going to the party and they're giving the hat check person their hats. Well, the hat check person had a little bit too much to drink over the course of the party. And so as people are leaving the party, he's handing them hats randomly. What's the probability you and your wife got your original hats back? That's one of the hardest problems I've ever worked on in my entire life, by the way. And I was able to come up with a solution. That is combinatorics. That kind of thinking. And so it's kind of cool. I'm bringing that up because at the end of the course, the last chapter we work on is going to be pure combinatorics and all the different types of problems we look at. And we'll see where probability fits in and all this stuff fits in. But it's also an idea that since if you're in this class, you're probably either a computer scientist or a math major, because there's not a whole lot of other majors that take this for the most part. And combinatorics will be a class that's probably in your future as an upper division student. And so you're going to get a little bit of background. I mean, a little bit of insight on the type of really, really awesome mathematics you do. There is no calculus. This is not calculus, but this is still high level reasoning and thinking. Okay, so that's how far I wanted to get today. So we will go ahead and stop.